Today we're going to talk about electric field lines in more details and look at more complex structures. So let's just review some things. So what is the electric field? Once again, the electric field is a set of vectors that show the effect of source charges on a hypothetical, and now here's the important thing, positive charge in a region of space. Okay, so it's imagining what's going to happen to that positive charge. What we're going to be doing today is putting out a couple of guidelines for electric field lines. And I know we're saying lines, but they are vectors, but that's just the way that they're called. So what is an electric field line? Well, we've said a couple of things so far. One, that they show the path a hypothetical positive, and I'm just going to use that for positive from now on, so I don't have to keep writing it out, particle would take in that space. Okay? Because they're just showing the path a hypothetical positive particle would take into space, remember, these things are imaginary. There's no real electric field line. It's a visualization technique. And I add this in, you might think, well, why am I obsessing over it? I never used to say that, and then it became clear to me that my students thought they were real things, so I just say it now. So they're imaginary, it's a visualization technique. It's important to know that negative particles would travel opposite field lines. Okay, because that's because of the way that the electric field is defined as showing what would happen to a positive particle. So we're going to leave it at that. I'm going to have a bunch of space here for some additional things to write down about electric field lines as we discover them. So here we go. So if I have a positive source charge here, so this source charge is nailed into place. We're not going to talk about what's happening to the source charge because things might happen to the source charge. I just don't particularly care about it. I want to see the effect of this source charge on everything surrounding it. Let's say our source charge is positive, right? And so therefore, the electric field would be a set of vectors going radially outwards from that source charge. Okay. Couple things there. You'll notice it's perpendicular to that surface. That's just what happens. But we'll talk about why a little bit later. So that's what that looks like. And I could keep on drawing them infinitely outwards. I just chose to stop drawing them after a little bit of space there. In fact, let's say that, let me put a box here, and that box is our field of view. And then I'll just draw them everywhere that they exist inside that box. Okay, right? So there you go. Now remember, these are imaginary, so I could have drawn additional lines. In fact, let me draw a second picture here with additional lines. Right? Because, once again, they're imaginary. They just show the path that a particle would take in that region in space. Right? So if something was there, that would be its path. Something was there, that would be its path, so on and so forth. Okay? Trying to be reasonably... Okay. Now, here we go. So, both these pictures are valid, but here's the thing. If I were to show you both these pictures, and I were to say to you, well, yes, the electric field shows what happens in this space. It's not that if we put something there that nothing would happen. These field lines kind of suggest what would happen. But what do you think these two field lines or pictures suggest? Right? Hopefully what you figured out is what this field line or this picture here is suggesting is that this source charge, we'll call this picture 2 and this picture 1, this source charge, Q2, is greater than Q1 in terms of its magnitude. They're both positive, but we'll just do that, right? Because that seems to be that this thing is suggesting a stronger field than this one. Why is it suggesting a stronger field? And it's not just because there are more lines. Let's go back up to this picture. Where would you say the electric field is strongest in this region? And hopefully what you said is closest to the charge. Well, how does the picture show that? Well, the picture shows that because if I look at the density of the field lines in a given area, that here I have more field lines in a specific area, here I have fewer field lines. That would suggest that the field is stronger here than here. If I make those same pictures here, right, you can see here that this is even denser than this, and this is denser than that. So closer things would have a stronger field, further weaker field, and that's something that we said before, that the electric field dies off as a function of 1 over r squared from the source. So we're going to come back here and we're going to have another fact about electric field lines. The density of field lines is proportional to the strength of the field. And so what do I mean by density? Just number of field lines in a given area. Once again, it's not a mathematical, like perfect 1-to-1 ratio there, but it certainly is what the picture is suggesting. And that's going to be an important tool for going forward for us, that the more field lines in a smaller amount of area is suggesting from that picture that the fields are stronger, and therefore, as a general rule of thumb, what do physicists do? We draw more field lines from stronger source charges. If we're doing a comparative picture, in order to make this fact about the density of field lines come out the way that it's supposed to come out, right? And so that's a convention that physicists use, because these pictures, once again, are just to convey information, to make predictions. So we should have a standard set of ways in which we interpret the pictures, and therefore a standard way in which we draw the pictures. Okay, cool. So let's go on to the next thing. So let's say I have, rather than one source charge in a region, I have 2. So I'll draw the first one here in blue and the second one here in purple. All right. And what would the electric field look like in a region with a positive? Actually, let's make it not a positive and a positive. We'll make it a positive and a negative, just for fun. Okay. Well, what would the field look like? Well, it might be very tempting to draw each of the fields independently. So let's say that this is the region that I care about. Sorry, that's a little bit not as good as I'd like it, but there we go. Right? You might want to draw the following. So here is source 1's. Okay, and then source 2, I'll draw in that purple. Now this is negative, which would mean that the electric field would go inwards, radially inwards towards this. Okay. It's not as neat as I would like. Okay, so we might think that that is the picture that we're supposed to do. Oh, actually, electric field lines. Let's go back and write some other basic information, apparently, that electric field lines go out of positive particles and they go into negative particles. Okay? out of positive into negative, because once again of the way that the electric field is defined. So what's wrong with this picture? I mean, granted, symmetry and sense of drawing and whatnot is terrible, but let's put all those sort of aesthetic concerns aside. What is wrong with the physics of what's going on here? All right. So any thoughts there? Let me give you a hint. This first bullet point, they show the path of a hypothetical positive particle would take in that space. Anything that's wrong? Hopefully what you figured out that what's wrong is this point right here and this point right here. If electric field lines show the path a positive particle would take, what would that mean for a hypothetical bit of positive particle drawn right, or that was placed right here? This picture would suggest that it has two paths, but that's not possible because the particle would have to go along one of those two paths. So then what does it do? Does it just choose which? And that's exactly what the flaw is. So therefore, we're going to come up with another really important fact about electric field lines, is that we never show electric field lines to cross or intersect. Okay? Because that suggests the particles have choice. And we're not going to allow a random bit of hypothetical positive particle to decide which way it's going to go. Nature will dictate which way it goes. So if that's a fact about electric field lines, I could go on the bottom of your list that we're making. Well, what does happen, because I do have two electric fields in this region. I do have two sets of vectors in this region that are overlapping. Well, what happens when I have vectors that overlap? And hopefully what you figured out is when two or more electric fields exist in the same space at the same time, you don't draw each field, you draw the, hopefully you're saying, vector addition of all the fields at each point individually. Meaning, to do this problem, we have to do the vector addition for every point in space in order to see what the electric field will look like. Now, we're not going to do that. We're going to do a couple of points in space and then extrapolate from there. But hold on a second. This should remind you of something. When two or more, and I won't say the word that's there, exist in the same space at the same time, you don't draw each blank. You draw the vector addition of all blanks at each point individually. What does that remind you of? And hopefully, allergies. Hopefully, what you figured out is that the law of superposition is valid for electric fields in the same way that it was valid for waves. When we had two waves at the same place at the same time, we didn't draw the individual waves, we drew the superposition of those two waves. Now, when we have two fields at the same place at the same time, we don't draw each individual field, we draw the superposition of those fields. I wonder if there's a connection between the fact that waves can superimpose and electric fields can superimpose, he asked rhetorically and sarcastically. The answer is yes, obviously, but we'll come back to that point later. So here we go. What are we going to do? We are going to do the superposition of those two fields as we talked about. So let's set this up. I have charge 1, which is positive, and I'm going to draw that in blue, right? And so everything about charge 1 will be drawn in blue. Next, I have charge 2, which will be that purple color, right? You might want to use multiple colors as well. And that's going to be our negative. And so I'm going to have multiple fields at the same place at the same time, and then what I'm going to do is in red, I will draw the superposition of those two vectors. Okay, and so what we're doing is we're drawing individual electric field vectors and then going for the superposition. So here we go. Let's pick a couple points in space. Let's pick this one first. That point is equidistant between the two source charges. So if I had to draw the electric field to just this positive particle at this point in space, that would be a vector that would go like this. And let's see, this is this is charge 1, so I would call that vector E1. Now, what's true about the electric field of this negative charge? Well, the electric field due to negative charges would go radially inward. Radially inward at this point would also be to the right. Now, this point is equidistant to the negative charge as the point is from the positive charge. So let's remind ourselves of something. What we're going to remind ourselves is that the electric field strength at a given point due to a point charge is K Q source over R squared. Since the R for both of these is equal to this point, and we're going to say that the magnitude of Q1 is equal to the magnitude of Q2 for the moment, then I would draw a vector of equal length as E1, and it would be going radially inward at this point, so there we go. So that's E2. And so what's the vector addition of them? All right, that would be, since they're both acting to the right, I'd have a longer vector to the right, and that would be the E net at that point, which I'll just will say is E, capital E, for the electric field at that point. All right, cool. So now let's examine another point. Actually, we'll examine another point along the line connecting the two charges. So let's say this point in space here. So let's first do the electric field to charge 1. Once again, radially outward from this point at this space. And I'm going to draw a longer E1 vector now, right, than the one here because it's closer. But due to the purple charge, it's still going to be to the right because radially inward, but it's going to be a shorter E1 vector or E2 vector because it is further from that. And then the net would be in this direction as well. Right, it's starting to get a little bit soupy there, but I think what, or hopefully what I'm hoping you're seeing is that any positive hypothetical charge placed between these two on the line that connects them would experience an electric force to the right, meaning I have a field line that goes from the positive to the negative. So I have this picture where I'm going to do the construction, and then I'm going to have a parallel picture here, folks, that kind of like hides the work that we're doing in between. So what we just figured out is that there is an electric field line that connects the two like this and goes like that, right? That anywhere along the line connecting them, that a positive particle would experience a force to the right. Now, would that force be constant? Well, the math seems to suggest that that really wouldn't be true. That gets a little bit more complicated, right? So because of the inverse squared nature of this, E1 got a lot bigger when you moved here, E2 got a lot smaller here, but the question is, would it be enough to, is the amount that E1 got bigger the same as E2 got smaller from here? That's a separate question and really outside of the scope of our course. That's something that you would deal with in a first level college course, to tell you the truth. Okay, cool. Let's look at another point that is not on the line connecting these two, right? Let's look at something over here. Well, if we look at this, E1 here radially outwards, right? So there's E1. And if I look E2, well, once again, E2 would pull rather a positive particle would want to go towards, radially inwards to that one, but it's going to be a smaller vector, and probably a much smaller vector to tell you the truth, because this is a lot closer to this point than this is to this point. The important thing here is that the net field in this direction would follow the direction of the E1 vector. Over here, I think we could kind of extrapolate there that the field due to the negative particle is going to be stronger than the field due to the positive particle here, and so the net effect is going to be like that. So if we come here to this, continuing along that, there is going to be a straight line here, but this one will be radially outwards and this one will be radially inwards. Awesome. So now let's go to a more interesting point, something that's not along the line connecting the two vectors. We'll pick another point that is equidistant between the two charges, but not along that line. So to this point is the same distance as that point. So let's look at the E1 vector. Once again, it's going to act radially outward from that point, and that is like this. So that is E1. Now E2, once again, radially inward. And because equal charges and it's equidistant, it's going to be the same size as the E1 vector, but just in a different direction. So what is true then about the vector addition of those two vectors? Well, hopefully what you're realizing is that if I were to do components here, because I would have to do the vector addition, the vertical component of E1 would cancel out with the vertical component of E2, because these are the same magnitude and these are the same angle up and down because of the geometry of the situation, yielding only the addition of the x components, and that would be the E vector net at that position. Okay. Let's pick another point in space. Let's say a point that's closer to E1, or the Q1 now. So once again, we would have radially outward from that point, and I'm just making it a little bit bigger than that one because it's closer to this charge. But now it's further from 2, so we're going to have a radially inward towards Q2, but smaller. So what happens with those two vectors when I add them? Well, the net resultant here, the y components are not going to cancel, so the net resultant is going to have a y component. It's also going to have an x component. Or you can just remember when I have two vectors drawn concurrently, meaning starting from the same point, that the resultant vector skews towards the larger vector. And so that's going to look like this, right? All right, let's do one more, and then from there we're going to extrapolate the rest of the picture. I'm going to pick a point that is kind of the mirror of this about the line of symmetry. Okay, so it's as close to 2 as this one was from 1. So if I look at this, the E1 vector is going to be smaller but radially outward. Okay, and E2 is going to be larger but radially inward. And therefore, our net resultant is going to skew towards the E2 vector, okay? And so if we think about that, what do we have? Well, it looks like a particle placed in this region would start to go away, but then kind of start curving in and back too, right? Such that this is going to be what the field line would look like. Now, if you notice, what's true about these E field vectors, the net field, compared to the line that I just drew in? Hopefully what you said, and it's going to be another fact for our electric field lines, is with when an electric field line is curved, the field vector at that point is a vector tangent to that curve. Okay? So there we go. So let's go over to our picture here, and what we're seeing here is a field that seems to do this, right? And I can draw in those instantaneous or tangent vectors at those positions. Now, symmetry would dictate that there is a field that goes like this as well. Hold on a second.